say like GRR vanishes, this cross term with GR, and the angular coordinate vanishes, and then maybe there's some determinate condition on the spherical part of the metric. Sigma tilde being the unit round metric. And if you furthermore impose the Einstein equations, well, sort of the hypersurface equations, then you find some metric expansion for the remaining components, for GUU, GUA, etc. And we talked about this BMS algebra, these vector fields, which act sort of as asymptotic symmetries and end up preserving both the gauge and sort of the fall-off conditions that one gets from the Einstein equations at null infinity. So that was sort of a very, very elaborate wind-up for today. We talk about something entirely different. Sort of at the end of the talk, we mentioned that there's some relationship between these asymptotic symmetries, or symmetries in general, and conserved quantities. And I think I gave the example of a time translation symmetry on a space-time background giving rise to some sort of conservation of energy for the wave equation. We also saw this in Pekin's talk earlier today. We also saw something in Yekai's talk that was quite interesting. We saw that given these super translations, and forgive me, I'm not going to reintroduce all this notation. There was sort of a notion of a conformal factor, its space-time gradient, and the pullback onto sort of Scri plus. This is sort of, we're sitting at null infinity, and then having this sort of as a function on the sphere, this alpha as some function on the sphere, say in L2. So given one of these super translations in the language of Garrosh, we were able to define these integrals of cross-sections. So supposing that partial sigma is some cross-section at Scri plus, we could sort of use this alpha that characterizes the super translation as a weight function and integrate it against the mass aspect. So again, given some asymptotic symmetry, we obtain, well, some sort of integral at null infinity, which encodes some information. And we say conserved in scare quotes because in the case of null infinity, it's not quite so that this is a conserved quantity. In particular, if I take the case where alpha is 1, we obtain just the bonding mass. Troutman's name should be included too. And we know that this is not conserved in the presence of gravitational radiation. That is to say, with non-trivial news. To give another example, which won't have any time to flesh out whatsoever, in this ADM formalism for asymptotically flat initial data sets. How do I spell? My goodness. So in this setup, there's actually kind of a totally straightforward way to define, the standard conserved quantities associated with the Poincare algebra. And this was known for quite a long time, whereas the picture at null infinity has taken, it's still sort of up for debate. these standard conserved quantities, say mass, angular momentum, etc. Map over to Poincare without too much of a headache. I guess there is a little bit of debate about angular momentum. So this Wald-Zupas paper is kind of amazing. I mean, it gives some sort of comprehensive approach. It tries to treat both the situation at null infinity and, say, the situation at spatial infinity. It tries to give some sort of coherent narrative for both, and tries to explain why in one situation you have a lack of conservation and in the other you do have conservation. And it actually works also for sort of to Muta's point during Yikai's talk. He mentioned that, well, this null hypersurface could be quite general. It doesn't need to be sitting at null infinity. It seems like you could simply choose any old null hypersurface, for example, an event horizon, and you could get some sort of measurement at the black hole, or of the black hole. Physics people are really excited about this because they can use these sort of charges to compute entropy. Another thing you could do is you could simply cut off a hypersurface in the space-time and make some sort of quasi-local measurement at a particular instant of time.
So you can interpret this Hawking area formula?
They're trying to, yeah. Yeah, I mean, I think Hawking's last paper before he died was computing this for Kerr. He computes some charges. So he has some symmetries on Kerr's event horizon. Using, I mean, very much, this is sort of the predecessor of everything that's come after. He computes some charges kind of using this formalism. The charges have their own sort of algebra structure, and they have something called a central extension that's associated with them. And the central extension, you could think about it, some sort of scalar pops out. And in the scalar that pops out, some sort of conspiracy happens, and what pops out is the entropy. Something like that. Yeah, I mean, I guess if the entropy is the surface gravity, then surface gravity and area are not so dissimilar. Okay, so let's try to get into this formalism that Wald introduces. Wald and Zupas. So they try to put things in a Hamiltonian framework. Their motivation being that the ADM charges were derived in such a way. So I guess we should talk about the definition and the existence of Hamiltonians. Yeah, and I apologize in advance. This paper is kind of maximally general. He's trying to put a lot of things under one tent. So I guess it reads a bit abstractly. It's not we're not doing things specific to null infinity quite yet. So let's have a fixed form manifold. Call it M, and some collection of Lorentz metrics. And these Lorentz metrics, let's just say they're smooth, and they're going to have some sort of, asymptotic conditions. So if we're trying to play the game at spatial infinity, we'd have some sort of asymptotic flatness in that sort of context. If we were trying to play this game at null infinity, we'd have, say, a metric expansion comparable to what you find in the standard Bondi-Sachs formalism. Okay, and the equations of motion that describe the theory are assumed to emerge from a Lagrangian. Which the authors take to be a 4-form in the background. So in particular, we're thinking about standard Einstein gravity. So we might take for a metric element G in script F the following. Well, the scalar curvature multiplied by the standard area form. And if we take this guy and we integrate over our four manifold, then we derive the Einstein-Hilbert action. Which somehow is going to lead to a nice description of the theory. You could compare this, by the way, to the derivation Pekin did earlier for the wave equation. He wrote down the Lagrangian for the wave equation, which was just its space-time norm, and then he took a variation to derive the wave equation. So yeah, if we sort of think about this as some sort of energy on our family of space-time metrics F, then we could look for sort of energy minimizers or critical points, namely things that vary to give us 0 for this integral. So if we take a variation, actually what we find is the following decomposition. And integrating this, what we would find is that we have critical points associated with solutions just like so. Now, this would be referred to as the Euler-Lagrange equation generally. And in the case of Einstein gravity, actually what pops out of this is just Einstein's equations. Okay. So in other words, solutions of Einstein's equations can be interpreted as critical points. Maybe you could think about them as minimizers almost of some sort of energy given by this Einstein-Hilbert action. What is dg? Oh, I'm sorry, this should be partial. Yeah, I'm taking some path of metrics and taking this as the associated partial. Okay. Oh yeah, everything. I'm used to thinking about a scalar Lagrangian, not a yeah. Well, I guess this is a 3 form, so I should multiply just this gadget. Okay. So in any case, we're actually not going to be so focused on these equations, the Einstein equations, but more so this extra term that pops out from the variation of Lagrangian. So the authors refer to it as the pre-symplectic potential. So they're thinking about it as a one form on this manifold of Lorentzian metrics. And eventually they'll take another variation to compute a pre-symplectic form, but it's the potential of that form. So to make it more concrete, and no time whatsoever to verify this, in the case of vacuum gravity, what we have is the following, where V is just like so. I should mention that whenever the Euler-Lagrange equation is satisfied, we have some sort of subset of metrics. So for G satisfying, these equations, we consider G as a part of this set script F bar. Right? These are referred to in the physics literature as being on shell. Something that took me a long time to figure out by context. Okay.
This L is just the original L, right?
This L is just my original L.
Just a scalar gradient. I mean, there is this given Hawking boundary term.
Right.
Because it's not.
You mean something like this?
You modify your Lagrangian a little bit.
Mm-hmm.
So when you do integration by parts,
Mm-hmm.
that will actually cancel the boundary contribution.
Mm-hmm.
So in a way, you're not assuming del G is of complex of 4.
No.
You're just assuming del G is equal to 0 on the boundary. So you're still going to have some boundary contribution that should be cancelled.
You're talking about, so if M had some boundary.
Yeah, but I'm just trying to figure out whether this L here is the one before the given Hawking multiplication or after. Maybe it's referring to the before the multiplication.
I think also there's, but if you had some variation of Lagrangian, couldn't you? Okay, so you're saying you would absorb it into the boundary term somehow if you modified.
Because in the original derivation, you're assuming del G is of complex of 4.
Mm-hmm.
Okay, and in that case, you're just not going to get any term. All the boundary vanishes.
Mm-hmm.
But if you really want to derive, some other expression, then you can only assume del G is equal to 0 on the boundary.
Mm-hmm.
So for example, you still have del G, the normal derivative.
Mm-hmm.
And that part usually does not vanish.
Mm-hmm.
And given Hawking actually find a term, basically just the integral of the mean curvature along the space-time boundary.
Mm-hmm.
And that can be taken to cancel those coming from del G, the normal derivative of del G.
Mm-hmm.
But I think here in their formulation, they're probably still taking the one that is before the given Hawking correction term. Namely, but this expression is probably still coming from
I think they are. But they discuss a little bit this ambiguity in the choice of Lagrangian. But I haven't made myself kind of the master of those details. There is, to get back to the sort of script, there is ambiguity here as well. Namely, if I had added some sort of exact 3 form to this, well, d squared being 0.
It's because it's boundary term.
Yeah. Yeah, so there's also ambiguity in this pre-symplectic potential as well. Yeah, sorry. Thinking about this guy as sort of a one form on the tangent space of script f. So we've introduced this notion symplectic into the word space. We need to actually fulfill the promise and take a further variation. Of our theta and anti-symmetrize. So we have now this omega defined just like so. And I apologize if this is hopelessly abstract. We're coming to a point very soon. So now you'd want some sort of 2-parameter path of metrics, and you're talking about taking directional derivatives in different order. And let me just mention that in the theory under consideration, namely vacuum Einstein, Wald gives the following expression. For omega, given the choice of theta that's occurred before. Of course, if you choose a different theta, then your omega would change accordingly. Let's see. And, sorry, P in this case is a projection operator that is just horrendous, or a trace operator in the metric that is just horrendous, and I'm not going to write it down. But the point is that for completeness, omega has the following form, assuming this choice of theta has been made. So with that, something's missing? Am I?
Del G2 should have some lower index.
Del G2 should have, yeah, it should. Let's see, what have I not contracted over?
BC.
You think BC? Yeah, it looks like BC. You're correct. I guess it makes sense since this probably has to contain the symmetrized part. Any case.
What is the projection? It's just this combination of...
Sure, yeah, I can write it down. It's not a big deal. Let's see. It is where is it? Oh, right, it's back here. Projection operator is yeah, I looked at it briefly and it didn't hit me. I wasn't enlightened by it, so I just thought to suppress it in the interest of time. But maybe it's worth chewing over. Let's see, 5 terms. Yes, 5 terms. Okay. All right, so another thing to point out is
To what space it projects to
this projection operator. I shouldn't have called it a projection operator. I mean, it's contracting over indices. I would just call it some sort of trace operator.
BC index should be symmetric.
Yeah, I guess I'm also reusing indices between these two. But I think that, I think that since you're contracting over everything, I mean, all you're really left with in terms of verifying that this is a nice all-3 form is just these 3, and then as a form over the as a form over script f, it's just a matter of the anti-symmetry of these guys, and they seem perfectly anti-symmetric to me. It doesn't seem, yeah, I mean, the projection operator doesn't feel like it speaks of anything mysterious. So what you could do with this is you could, I mean, now you have a sort of a pre-symplectic form omega, and you could mod out by the degeneracy that it contains to get a proper symplectic form if you wanted to. We don't really need to go down that road, though. What we're going to do instead is, well, first we're going to mention that one way to generate metric perturbations or variations is to take a vector field on the background. In particular, you should be thinking about the asymptotic symmetries that we've been discussing. And if you take, I guess all I want to say is if you take metric G and you've got X, some vector field on your smooth manifold, well then, you're going to be interested in the vector fields that are tangent to script f. Now, given that script f, probably erased it by now, contains your, yeah, I have. Given that script f contains your fall-off conditions, you've already sort of restricted yourself to these specific vector fields, like BMS. Given that script f, which contains all these metrics, not just solutions of Einstein's equations, contains still these fall-off conditions already C has been restricted down. It's not just any old vector field. Moreover, I guess I should mention if G happens to be in the solution set, or happens to be on shell, so too will its variation in the direction C. What do I want to say? It's in the tangent bundle of script F bar. It's making my head hurt. See. Yeah, I mean this is just the natural fact that if I have a solution of Einstein's equation, and I take a variation of it along any vector field, actually, not just one satisfying asymptotic symmetry assumptions, then I get a new solution of linearized vacuum Einstein equations. Okay, so in any case, it makes sense to sort of slot this sort of guy in as one of these metric perturbations. It could be that delta 1G is, in fact, a variation along a vector field. Makes perfect sense to say such a thing. Now, given all that, we're ready to provisionally define a Hamiltonian. So given some vector field C, hypersurface sigma, and we can define, or we can attempt to define, the Hamiltonian conjugate to C via, well, really, we'll give a formula for its variation on script F, with the hope that this expression on the right-hand side is actually, in fact, integrable. Not obvious that it'll be so, and in some cases you'll have non-existence of a Hamiltonian. Okay, so we're hoping to be able to define the Hamiltonian. Sorry, Hamiltonian is given by some map like so, and we're defining it via its variation. The hope is that we can write this expression, say, as delta of some big nasty integral. Okay, such that this thing is actually integrable, and it makes sense to make such a definition. Okay. Oh, I guess I should mention that we need this to be possible. We need this formula to be true for all G in the solution space. So just for G that are on shell, think solutions of Einstein's equations. So just skipping way ahead, it won't always be the case that this is definable, at least with a naive approach to things. And if one looks at the situation at null infinity in the Bondi-Sachs formalism, I'll just remind you from what I spoke about last time. In this Bondi-Sachs formalism, given you have some data at null infinity, say a mass aspect m, an angular momentum aspect n, and a shear tensor c, and with this shear tensor giving you, as its u derivative, the news, which somehow encodes gravitational radiation. If one has such data, and moreover one considers this BMS algebra as parameterized by pairs f, y, a, f being sort of the supertranslation function, and y being a conformal killing vector field on the unit sphere, what happens when you actually go to do such a calculation is you find, I guess I should say, This is taking a hypersurface sigma, which is, say, in this bond exact coordinate system, just a constant u slice with some cross-section partial sigma. And what you find in the end is, let's call this z, where z is some linear combination of the two. Then what you find is the following. You sort of find an integrable piece, which looks quite nice, followed by disaster. A non-integrable part that's sort of modulated by the news. So let's see what we find. A nice integrable part, like so, and then a part with the news rearing its ugly head. Okay. Interestingly, both of these terms can be expressed as boundary integrals, something we're going to get to just a little bit. So there's a part of it that looks quite nice. We could sort of imagine integrating this formula and really finding a Hamiltonian associated with z if we just had this piece here. But unfortunately, in the presence of gravitational radiation, that is to say with the non-trivial news, we simply have a piece that can't be dealt with in this way. This H in the left-hand side, there is. Oh! You mean in terms of this definition here? I believe so. Yeah, I believe there's definitely dependence of this guy on del G. It definitely depends upon the direction you're going in. Also, I probably should have said something like, it turns out, as I mentioned, this formula here can be rewritten entirely in terms of this boundary cross-section. It turns out that for any reasonable Hamiltonian that we'll talk about, you actually don't so much need the hypersurface, you just need its boundary. You'll always be able to write this guy as a boundary integral. This is, by the way, this formula is from many years after Walt's paper. This is from a paper of Bartnik and Trissart. I think it's called BMS charge algebra. Okay, so what we need to do now is we have a definition of a Hamiltonian, but it's not totally satisfactory. Naively, at null infinity, let's try to get some sort of notion for what are necessary and sufficient conditions for the existence of a Hamiltonian, and then use those to understand sort of the space of modifications we could make at null infinity to get something quite nice. I mean, the answer is it's kind of boring. What you do is you sort of add a counterweight to this, such that you've it's almost like you just ignore this and you just have the integrable piece. But in any case, Walt's formalism is very, very cool and very general. So let's go through with it. We're talking about F. This F here. Yeah, this script F is the space of Lorentz metrics with smoothness and with appropriate asymptotic conditions. On M, yes, yeah. And omega is a symplectic form. It's alternating in these two indices. You could think about it as a symplectic form on script F. right? Because we've got these two different covector directions, so to speak. But yeah, it's a little much calling it a pre-symplectic form on this bizarre manifold. Okay, so let's try to get some notion. Necessary and sufficient conditions for the existence of one of these Hamiltonians. So the authors introduce at this point the Noether current. I'm probably forgetting some accents on some vowels in her name. But they define it like so, in terms of theta and the Lagrangian. So it's sort of a one form on F, on script F. And here we mean the Lagrangian, and we're taking the interior derivative. That is to say, we're just slotting this in to the first component of L, thought of as a tensor. So it turns out that J can always be rewritten. This is just something that Wald and Zupas quote in the literature. Can be rewritten in terms of a Noether. Let's see. So which one is the current? Is this a Noether? Let's see. Anyway, they simply rewrite J in some new form. So in terms of this quantity Q, and something extra that depends upon or encodes the constraints of the theory. So I'm thinking of something like the constraint equations for an initial data set, if I'm looking at the asymptotically flat spatial infinity type situation. So there's some sort of alternative decomposition of the current in terms of Q and C, other than its sort of definitional decomposition in terms of theta and L. Right, the C vanishes for G in the solution space. That is to say, if G is on shell. So in our situation, vacuum gravity, it turns out that Q is just like so. And of course, this is again contingent upon the choice we made earlier for theta. I guess, yeah, this current is associated with a choice of vector field deformation, C. So given C, we can define Q. Given Q, we can arrive at J, at least if we're on shell. Okay, so it's a one form. So whenever you have C, the variation so it's a function of G and the following variation of G.
Q is independent. Q only depends on G, not the variation of G.
It depends on this variation of G. Well, this is if you you're talking about, so for example, this Q?
Yeah.
This Q depends upon the variation of G in the sense that G is being varied by C, the vector field. Sorry? Uh-huh. I'm sorry. That's where the confusion's coming from. Yeah, that's my mistake. The variation we're thinking of is, yeah, the variation along C. Yeah, thanks for that. So it's sort of just like that we have two different ways of writing the same thing. So if we take the variation of both these equations, something interesting is going to come out. And what goes on is that if we take the variation of J, well, with the first formula, what we find is just like so. And assuming that we're on shell, this can be rewritten in terms of the the Euler-Lagrange plus this additional d theta. And using Cartan's formula to commute these interior and exterior derivatives, what we find in the end is it's L of C theta of G delta G plus d of this contraction from the interior derivative. Okay. And this gadget here is nothing other than omega applied to the metric variation and this variation along the direction C. So we're getting at a way of rewriting omega in terms of this Q. So from the previous board, what we have I actually can't remember the exact order of these indices. It would just be a difference of a sign in any case. Okay. So, in other words, we have moving this gadget over here and looking at our other formula for the current, taking variation a bit, and, well, these constraints vanish when we're on shell. Let's just assume that the variation we take remains on shell. Actually, let's just assume that we're talking about a linearized solution as well. Then what we find in the end is, let's keep it free, as I've written it in my notes. We move this guy over. We have the variation of the current with the other formula. Just like so. Yeah, in particular, if G is a solution, and moreover, we allow our variation to remain tangent to the solution space, then this final term vanishes. And supposing we had a Hamiltonian, if there existed a Hamiltonian, what we would find is that it could be rewritten purely in terms of this boundary integral, right? Of the variation of Q and a contraction of C with the presymplectic form theta. So this explains a little bit how in this calculation at null infinity earlier, we wound up with just a bunch of boundary terms for the cross section, rather than hypersurface terms. Okay. Now again, assuming this here, we could take a further variation and equality of mixed partials, I guess it's Clairaut's theorem, would give us some nice necessary condition for the existence of a Hamiltonian. So if we have a Hamiltonian, and given that this formula is always true, we've written the Hamiltonian charge like so. Taking a further variation, equality of mixed partials gives us 0 for this left-hand side. And now varying this integral in the interior, we get some necessary condition on omega and C. So we need the vanishing of this integral here to have any hope of defining a Hamiltonian. And it turns out this is not just a necessary condition, but it's actually sufficient. And the authors kind of contrast two different situations or scenarios. The first is a situation where, well, we're imagining ourselves on some hypersurface with, this is not a real boundary. We're talking about going out to spatial infinity or to null infinity. This is to be interpreted as some limit of compact surfaces with boundary. And the limit of those boundary integrals. In any case, the first situation involves omega decaying appropriately as we go out towards infinity, such that omega just vanishes in the limit. And that's sort of what happens at spatial infinity with standard asymptotic flatness. So that this guy vanishes, necessary and sufficient conditions fulfilled. And we have a nice definition for these conserved quantities in the ADM formalism. And the other circumstance, of course, has omega non-vanishing, as it does at null infinity, in such a way that we can't really define the Hamiltonian in a straightforward way. And even if we could define it in a straightforward way, what you would find is you'd find some sort of flux. You would find a lack of conservation, as we see in the Bondi-Troutman mass. Let me just write the definition down. Okay. All right, so if we had decay of the presymplectic form omega at this boundary cross-section, that's the case in the ADM formalism. Spatial infinity. Another possibility is we could do this even at null infinity where it doesn't decay, supposing that C was tangent to this cross-section in such a way that, well, if you take this contraction, you've got a 2 form that you're integrating over the surface, but remember that omega was already a 3 form, and you've introduced one tangent direction already slotted in, one tangent direction to the surface. In other words, the sort of pullback of this total quantity onto the surface should vanish. Okay, the author sort of formalized this a little bit. So let's attach a boundary. Call it B, Tim. This is in much the same way that the Echi did. I mean, if you wanted to be super careful about it, you define some, say, unphysical space-time as the union of M with a boundary, and then play some diffeomorphism game. But we won't go too much into detail. I guess I just want to say that we're interested in the vector field C that preserve G, the conditions on G at B. So in a very vague way, we could talk about sort of, a conformal metric, and we'd be interested in C that preserve, say, fall-off conditions in this conformal metric or something like this. Let's see, what do I want to say? So regardless of whether we have a Hamiltonian or not, it's still possible to write down the current. Assuming that we're on shell, and that we have a C that preserves the structure of G, always possible to write this fellow down and to integrate it on a cross section, the hope being that it's integrable. The thing I wanted to point out, though, before going into the modifications that one would make at null infinity, is that assuming that we had vanishing of omega on B, what you would find is, given two different cross sections, say partial sigma 2 and partial sigma 1, Hamiltonians, of course the Hamiltonian will exist in this circumstance, would have a difference of just 0. So remember that this Hamiltonian here is just going to be given by a formula like so. And likewise for the first surface. And the point is that although our mental picture is we've computed them by taking null hypersurfaces, sigma 2 and sigma 1, we could secretly just use the interpolating boundary surface, say B12, and rewrite this as the integral of B12 on B12 of omega. Okay. Actually, I guess I shouldn't have drawn this picture at null infinity since it's not true at null infinity. This is more a picture for sort of a blown up version of spatial infinity, where at 2 different times, on 2 different time slices, we can compute the difference, say, of these boundary integrals for ADM mass and find some conservation, owing to the vanishing of omega on the boundary. Oh, sorry, I think should be saying that. Let's see, so, right. This difference should be the difference of these 2 integrals. And then the point is that we reinterpret as B12, right? Okay, yeah, and in the circumstance where omega doesn't vanish, but say a Hamiltonian still exists, we would still be able to rewrite the difference of these boundary integrals in this way in terms of B12 rather than the 2 null surfaces that gave rise to them. But now omega would be non-vanishing in this second circumstance. Say if sigma were to be tangent to this boundary surface. Okay. And this is sort of what happens at null infinity. We do get some sort of flux, some sort of difference as retarded time advances. So now we want to turn to the modification of the sort of naive Hamiltonian, with a naive formula that you might try in Einstein gravity. In order to get a Hamiltonian that satisfies these necessary and sufficient conditions, right up here. So the modified Hamiltonian that Wald and Zupas propose is really pretty simple. I guess they call it script H to distinguish between it and the sort of naive Hamiltonian, just standard H. So let's define it by extending omega to this boundary surface B with pullback omega bar. And given this omega bar, they define some symplectic potential on this total manifold M with boundary as follows. Namely, omega should be just like so with respect to capital theta. Okay. And with this definition, they define the variation of their modified Hamiltonian just like so. Again, for a hypersurface with cross-section sigma. Oh, sorry, this is lowercase theta, and this is uppercase theta.
Where's the modification?
Where's the modification? So the standard Hamiltonian has these two terms here. And what we've done is we've added on this capital theta in such a way that when we check this necessary and sufficient condition, this is cooked up in such a way that taking its variation and alternating, we basically get from it a term that will kill this bad term here. So generally speaking, this will leave for H, I guess I've written it here. For H, it'll leave something of the form with this presymplectic form omega. And we've cooked up this presymplectic potential, capital theta, in order to kill off that term. Right, so this necessary and sufficient condition, which looked like C contract with omega, now has some counterweight. Sorry, it looked like negative. C contract with omega now has some counterweight. Z contract with, again, if you took alternating variation of this, you get this omega bar. The pullback onto B. Okay. Yeah, I guess this guy is being pulled back as well, secretly, since this is defined in terms of some limiting process. Okay. Yeah, so I mean it's kind of the duh modification. You naturally modify it in such a way that the necessary sufficient condition is satisfied, kind of almost vacuously. It's not to say though that this capital theta cancels theta. They could be quite distinct from one another and still give rise on the boundary to the same presymplectic form when you take the alternating variation of the two. Okay. In terms of the sort of the naive way to think about it, though, it's that, okay, now I've gotten to obviously something that's integrable. It's almost like I can just pull this delta right out. Roughly, you could think of these guys as canceling one another. But I think the reality is more so just that the symplectic forms associated with them do equal one another. Okay, let's see what. So yeah, as I mentioned, this modified Hamiltonian sort of naturally satisfies this necessary and sufficient condition. So it is a Hamiltonian. It is a bona fide Hamiltonian, say, at null infinity. There's a little bit of bookkeeping to do, though. Namely, you need to normalize this guy. So you've defined something's first derivative, but you need to sort of specify it at a point. You need to give some initial conditions for the function described by that derivative to be well specified. So, in other words, you need to choose a reference. So integrating, it's possible to define some conserved quantity for the solutions of Einstein's equations up to, you need to fix this thing up to a choice of reference solution. You know, where you're expecting the Hamiltonian to vanish, say at this reference. And the reference, I mean the natural one that comes to your mind at null infinity in the situations we've been talking about would be Minkowski. Now, if you wanted to play this game in curved type backgrounds, say an ADS type setting, so negatively curved spacetimes, then ADS would be the appropriate thing. If you wanted to play this game at the event horizon, then Schwarzschild might be the right thing. But the choice of reference, it's sort of like the choice of asymptotic conditions. It's very specific to what you're wanting to do. Okay. You're saying to with this being defined, yeah. Yeah, that's how you would integrate it to get the Hamiltonian. I mean, the real thing is that remember the formula I wrote down earlier. It was it's going to be something like for C a pair of translation and rotation. It's going to be something like this when you compute this variation. And then you just erase the variation. I mean, and this does vanish in Minkowski with any Bondi-Sachs data, actually. So some game like that, yeah. I must say, though, it's written in a somewhat abstract way. So there's still a little bit of residual ambiguity. We fixed this reference solution, but there still is some ambiguity. Oh, and I guess I should say, we talked earlier about how, so way back at the beginning, we had the Lagrangian giving us the Euler-Lagrange equations, and our pre-symplectic potential, theta. Now, we mentioned that you could always substitute in any sort of exact form, and this equation would be unchanged. So I guess one way of getting around it, and if you took the alternation of this, took the partial of it, or varied it, then alternated it, likewise you would have some sort of ambiguity in omega. I guess my suspicion, though, is that, and the authors don't really talk about it too much, but my suspicion is that this business of fixing a reference solution, you could sort of make whatever choice you like, and as long as you want to zero out Minkowski, say, in your Hamiltonian, it would sort of be fine. But this would come out in the wash. Okay, but just wanted to put that out there.
This integral doesn't vanish if the Minkowski is super translated.
This integral doesn't vanish if Minkowski is super translated. Oh, you're talking about the center of mass?
Yeah.
Yeah, I guess there is some additional issue with how do you call it? Choosing having not just G0, but how do I say choosing the right one of these? I guess they mentioned that you need to be a little careful. You want it to vanish on a particular solution, but when you take a variation of it with an asymptotic symmetry, you should sort of get the same thing. I mean, I know that the data changes, that it picks up a shear, but you should sort of get fundamentally the same thing. Should be the same space-time, so that should also still vanish, but that sort of over-determines the Hamiltonian. There's some discussion of that. I think the point is, though, that we could take some ground Minkowski. Say there is some sort of standard Minkowski. But I understand what you mean, that it's possible to change, to super translate this piece. This is what Yuka is saying. In such a way that you got something that was sort of non-trivial as a ground state. I think just choose the standard Minkowski.
Do they talk about BMS invariance?
No, they don't talk about BMS invariance.
So you still heavily depend on
The choice of reference?
yeah.
Yeah, absolutely.
Or the coordinate system where they write out.
The coordinate system.
Write out the G,
Uh,
I mean, when they talk about Minkowski, they always refer to this Minkowski with the standard coordinate system.
uh-huh.
I mean, that's just
Actually, I mean, I also think, if you remember, this is not a proper subgroup, it's a quotient group, as you told me. I think you could also play some game with this, maybe in such a way that this would go away, and you wouldn't have any troubles, even if you had any Minkowski. You would just have to choose a different parameterization of your Lorentz algebra. I'm not sure. Maybe. Okay, but anyway, there's some there's some leftover ambiguity, even having fixed all this junk. Let's see what I want to say. Right. If you took this capital theta with the condition on it that its alternated variation gives you the pullback of omega to the boundary, there's still ambiguity in the form. It's actually sort of the same story for this earlier guy, but now we're talking about a different sort of variation, a different sort of manifold. It's sort of defined up to sort of an exact one form, or an exact form. Now with the exactness being discussed on the solution space rather than the manifold. So this is the exterior derivative on M. This is a variation on F. Okay, so the point is that this would obviously, if you took its alternation, obviously gives you nothing, right, because of the quality of mixed partials. Okay. So given that this sort of flux integral is true, and will still generally be true once you've defined this sort of souped-up Hamiltonian, well, you're still going to have this issue. The authors want to pick theta in such a way as to accommodate this flux. They want to sort of normalize things. So, given that you're naturally going to have some flux, they call it FC, will occur. Authors want to choose capital theta such that f of z vanishes in the absence of radiation. And for them, kind of in a puzzling way, they're really interested in it vanishing for stationary solutions. So stationary solutions certainly are not radiative. They don't have any news. But it's actually a little bit strange that that's their choice, given that there are solutions that are not stationary, but also not radiative. But in any, sorry?
What is that? I didn't really read. Given flux?
Oh, given that there's a flux that will occur, and I haven't defined flux, and I keep writing z in a kind of a mangled way. Sorry about that. Given that flux will occur, there's going to be some sort of flux that pops out of this Hamiltonian when we integrate over different cross sections, different retarded times. So given that such a thing will occur, is there a way to sort of use this ambiguity in theta and choose it appropriately in such a way that for solutions which oughtn't to have flux, like stationary solutions, well, they won't have any flux. This is their idea. They want to wiggle this thing around such that, say, in Kerr, there should be no gravity, where there is no gravitational radiation, there should be no flux in your Hamiltonian charges. Okay? Well, yeah, I mean, it would depend upon what you're doing. You're at null infinity and in asymptotically flat settings, Kerr is appropriate. Maybe if you're in a curved background, then de Sitter is appropriate or something. I just don't like it because it doesn't seem to include every single non-radiative solution. There could be other solutions, beyond the stationary ones. But anyway, it's not my definition. How long do I have? Okay. So let's calculate this flux for this new Hamiltonian, script h, on two hypersurfaces. I hope I still have the picture up there. Yeah, I do. This is sort of the picture in your head. And the flux is really just defined as their difference So we define the flux like so. Well, we define its variation, I should say. Again, getting ourselves maybe into trouble. What happens is, well, if you take this formula, given that it's some straightforward modification of the earlier Hamiltonian with this extra term, what you find is you could rewrite this as a boundary integral of the pullback of omega plus this exact term. Where capital theta comes into the picture, this new presymplectic form. And I think, again, we're going to use Cartan's formula for this interior and exterior derivative commutation. So what we find is just let's see, why have I rewritten it like so? What happened to the interior derivative? Should also have a term like so. Now, where did it go? I can't actually recall why this term drops out. In any case, this was rewritten as this pullback. Remember that this is basically where this is just my original metric variation, and you could think about del 2 as being now the variation in C. So we can rewrite that now in terms of omega, like so. Okay. So we get cancellation. Our pullback omega is canceled by so. And so, in other words, our flux on B12 which, I mean, of course, is just defined as the difference of these two Hamiltonian charges, is really just given by the variation of capital theta. Okay. In other words, let's say this is true for every single pair of charges, and so in other words, it's true for every single little interval at null infinity. The flux can be defined purely in terms of this presymplectic form, capital theta. And so what one does is one just imposes, however one's going to define this theta, one imposes that it should vanish for all these stationary solutions. Okay. Let me just try to quickly go over now the last third of the paper where he gets into something a little bit more concrete. And it's actually sort of in the same notation that Yikai employs, or employed in his talks, in this notation of Garosha's paper from 77. So let's just remind ourselves that we have some unphysical metric say G tilde is equal to omega squared GAB, omega being this conformal factor, which describes the boundary, and in the Bondi gauge, which we assume, remember that there's this freedom in the choice of omega, the conformal factor. We'll assume that the Hessian of omega vanishes, recalling that NB is just the gradient of omega. Yes, remember that the boundary is thought of as the zero set of omega, its derivative being null and non-vanishing. Okay. Now, given some unphysical metric perturbation corresponding to a physical metric perturbation, so delta G AB tilde can always be rewritten like some omega times TAB, where TAB is a non-vanishing tensor on the boundary. So a lengthy calculation yields the following result for omega. Which remember ought to be alternating in these two metric variation directions. So here we have the pullback of the volume form to scribe plus. Here we have metric perturbation 1, metric perturbation 2, and here we have this operator SAB that Yikai mentioned, which is specified by the following formula. Yeah, it turns out that using the fact that, remember that the news in his formalism was rewritten in terms of this, S bar rho AB with rho defined in terms of the pullback metric like so. It turns out that you can rewrite omega as, the pullback of omega as so. So purely in terms of the news and the metric perturbations. In such a way that the appropriate theta to add, whose alternating variation gives you omega bar, is just like so. So this theta is sort of the new term that's going to appear in our Hamiltonian definition. It's going to be some sort of correction factor. And I guess I erased earlier, but this is roughly what happens. Before this, when you took the sort of naive Hamiltonian, you had all this stuff plus a term involving news, so some non-integrable term. And the point is that now you've added something involving the news in such a way that this term is sort of counteracted, in such a way that this non-integrable term is counteracted, and you finally have something that is integrable. In the rest of the paper, and I should mention that for stationary solutions, the news will vanish. And in fact, again, as I mentioned, there are more solutions for which this is true, but in particular for stationary solutions, this is the case. And so this sort of normalization that Wald and Zupas propose of choosing theta in such a way that there is no flux for these solutions does pan out. And in the rest of the paper, what they do is they use this formalism to rederive Gaussian supertranslation charges that Econ presented to us. Oh, oops. So probably one of the reasons that they enjoy his formalism and use it in their paper. The other thing that they do is they make a calculation of angular momentum and find more or less agreement with these guys, Dre and Struble, I think their names are. So let me just mention. For supertranslations, they recover Gaussian from 77, and for Lorentz algebra, they find some sort of connection to Dre Struble. These are two authors who had tried to make a definition of angular momentum based upon Penrose's formalism. It's a little bit messier here. I think it's less straightforward owing to the fact that there's not really a clear choice of Lorentz algebra to make, given that the Lorentz algebra sort of appears more naturally as a quotient group rather than a subgroup, or a subalgebra, quotient algebra, sorry. But anyway, they find some daylight between these two notions. But I think the best thing about the paper really is that it's been cited a few hundred times because it's just so general. You could take it, you could do a calculation at the event horizon, you could try to make some quasi-local definition, you could use it in curved settings with a cosmological constant. Yeah, so it's quite flexible. I think I'll stop there.
Any questions?
So in classical field theory, you also have the type of Newton.
Mm-hmm.
And when you compute charges in the same way,
Mm-hmm.
what is the difference of this approach from standard compute theory?
I've got the faintest idea. I mean, to me, I was wondering where the hell are they coming up with this omega and this theta. I had no idea. I mean, where they came up with this stuff.
Standard symmetry, they are just usual particle field theory.
Mm-hmm.
It's very standard. But now you have asymptotic symmetry. So what is the generalization as given this approach?
Generalization.
So if these are standard symmetry, then the classical field theory tells us how to compute charges in very much the same way.
Uh-huh.
So what my question is, in which cases do we generalize the classical field theory framework? Because now the symmetries are not standard symmetries.
I feel like, but you're saying that, okay, if I had a space-time with a global killing field, then I can make some definition. Is that what you're saying? That there's some standard, straightforward way if I have a global kill?
When you talk about film theory, there's already a metric. So
Uh-huh.
I'm talking about field theory, where the field can be anything.
It would be
You
incredible.
work on a fixed space. You have a fixed metric here. Here metric is a variable.
Right. In field theory, the metric can also be.
The other thing that would be difficult in terms of if you can do this in field theory for exact symmetries is that there's almost no metrics with exact symmetries. I mean, so it would just be a very impoverished theory that you would have. You'd be able to do a few calculations, I guess. But if you didn't have asymptotic symmetries, I mean, you wouldn't be able to take Bondi-Trautmann mass, for example, because most spacetimes don't have exact stationarity. If you needed to have exactness from what you're saying.
And you don't really have a Lagrange in this case.
I need to check that.
But the scalar curve is secondary field there. It's different from classical field. When you are only zero, you are not a
It's a special case.
Yeah, just from what you're saying, if you can only do it with global symmetries, then yeah, you just have to have asymptotic symmetries to make any measurements at null infinity for the vast majority of spacetimes. So, yeah.
So C is related to X and Y,
Mm-hmm.
which are not global.
Yes, that's right.
So in what sense LC of G is a vector field of X?
LC of G
LCG
is a two tensor.
is what is the vector field of X?
So we're talking about C on M, or are we talking about? Okay, this quantity on.
So this is supposed to be a vector field of X.
It's supposed to be.
But
Well, on the
C-
tangent space, yeah.
Yeah, but well, G can change. But
Mhm.
C is not global.
Probably, I would just say you could choose almost any extension of C away from null infinity in such a way that it had nice asymptotics. So I would just say, okay, I want C to have this asymptotic form if it's a super translation. Oh, I don't know. I'm going to get myself in trouble. But you see what I mean? I mean, its structure and its form near null infinity matters quite a lot. But beyond that, I could just choose probably any old extension of it, and I'd be fine. As long as it has this asymptotic form, I'm okay. So I would just define an arbitrary extension of it, more or less, as long as it had this asymptotic behavior.
Because your Y is supposed to be a local conformal.
No, okay, for super rotations, it's another ballgame. Yeah. I mean, I'm thinking about YA as being global. Yeah. I mean, I barely had time to roll out the abstraction, let alone think about super rotations. That's for another day.
So then you avoid it and then other charges.
Yeah, that's true. I think it should be mentioned, though, to your point last time, that when you talk about these super rotations, the only successful people so far have done some kind of game like they try to define these charges in this Hamiltonian framework. And what they get for a cross-section is they get an O1 piece. This is assuming they're taking a slice and taking R goes to infinity. I just want to mention that they sort of get the constant order piece that they want, then they get this term with linear growth that seems to be diverging. And more or less what it looks like is so they get the variation of the shear tensor, take its divergence, and take y. And what they do is they basically just integrate by parts, which you can't do for a local conformal killing vector field. You would have to worry about some sort of residue or something like this. You have to worry about some boundary term. You can't, it's not smooth and globally defined. And from here they use the CKV equation and the tracelessness of this to say that this divergent term isn't a problem. I haven't really seen a successful strategy that really deals with the local CKVs in like a rigorous way, but that's a big digression.